We come to you in prayer to firstly thank you for allowing us to see another day, Lord Jesus. Thank you for allowing us to be in the right frame of mind to be here today, Lord God. Thank you for providing us with the resources as well and the knowledge and the intelligence for these persons to help us for our upcoming CAPE exams. Lord, as we go through this session, may it be informative and let every single student in here learn something new or even recall some information. We ask that this be a blessed and very informative session. In your most holy and righteous name, we pray. Amen.
Amen. Amen. Okay, so welcome students to this in our first CAPE Chemistry Student Camp. I hope you have come prepared to participate, all right, and to concretize some of that knowledge that you've been working on for chemistry. So today our presenter for this session, as well as for the session tomorrow, is Mrs. Nadine Ellis Hall. She is, in fact, a master teacher in chemistry and has been doing that and has been holding that title since 2007. Now, she has operated at all levels of the examination process. She has and currently serves as moderator for chemistry for CSEC and CAPE. She's also worked as marker and examiner for CAPE Chemistry. She presently teaches at Cornwall College, and I am sure you would agree with me that she is very qualified to take us through this process this afternoon. So help me welcome Mrs. Ellis Hall. All right. Welcome, Mrs. Hall.
Thank you very much,
Okay.
Dr. Taylor Campbell, and welcome students as we go through just one of the few topics that are slated to be a part of your paper 2, and one of the many topics that are slated to be a part of your paper 1 for the examination. Now, today the topic that was selected is rates of reaction. The format, I will be doing a revision. Hopefully, it's a revision for most persons. You would have done this already. You're familiar with the information. You have reviewed the information, and all I'm doing is just concretizing the areas that you are not so sure of. Once I have done that, then we will go through some past paper questions that are based on rates of reaction. If you have a question, a query, or anything like that, raise your hand, and Miss Dr. Taylor Campbell, you will unmute for me.
Yes, I will operate this side. Right. So students, please respond in the chat when Mrs. Ellis poses different questions, or if you have comments, and if you want to ask a question, you raise your hand. Okay.
Right. All right, so let us get to it. And I'm going to turn off my camera. I just wanted you to see my face for the first part. And I'm going to turn off my camera. And I must tell you that in where I am in St. James, it is overcast and raining. I hope I don't lose electricity or internet. But if I do, I will definitely send a message to Dr. Taylor. All right, so let us look at the objectives associated with rates of reaction, and these objectives come directly from the CAPE syllabus. So we're going to be explaining the concepts associated with reaction rates, including rate constant, order of reaction, half-life, rate determining step, activation energy, collision theory, and catalysis. We're going to look at the designing suitable experiments for studying the factors which affect rates of reaction, construct rate equations of the form rate is equal to K times the concentration of A raised to the power N times the concentration of B raised to the power M. We're going to limit these to very simple cases involving zero first and second order reactions. We are going to deduce the order of reactions from appropriate data, interpret concentration against time and concentration against rate graphs for zero and first order reactions, perform calculations from rate data, perform simple calculations using half-life data, and explain the effect of temperature and catalyst on the rate of the reaction using Boltzmann distribution of energies and collision frequency. Now, I will not be going through the objectives in the order in which they appear in your syllabus or here. Certain objectives can be grouped together, and when grouped together, they make more sense than how it is that they're set out as objectives. But at the end of the session, we should have gone through everything that is listed there. All right, so everyone basically they should know the definition for the rate of reaction, as this is something that you would have learned from CSEC. And so I've put that one there. And I am going to ask for the other two. What is rate constant? What is order of reaction? And if I can get a volunteer. So rate of reaction is the change in concentration of a reactant or product with time. Can anyone tell me what is the rate constant? Raise your hand so that Dr. Taylor Campbell can unmute your mic. Any volunteer?
They can also post in the chat, all right?
Right.
All right, I'm not seeing a raised hand yet. Okay, students, you want to raise your hand or post your answer in the chat, please? Okay, so we have a Monique Robinson.
Miss, is this the thing that remains constant even when the rate changes?
Well, for a particular reaction, yes. Anyone else? Brianna Tingling hand is raised. Dr. Campbell?
Yes, I'm trying to unmute her. Yes,
Good
she's
afternoon.
unmuted.
I have the rate of reaction is the consumption of reactants and the formation of products.
Oh, it's the rate constant we are defining. The rate constant. All right. So we're going to come back to this slide. I'm going to go through and I'm going to see if you can come up with a definition based on what we do.
In the chat, somebody has the proportionality constant in the rate equation.
All right,
and
that
somebody
is
has
true.
Rate constant K quantifies the rate and direction of a chemical reaction.
All right. And please keep in mind these definitions and let's see if they're correct as we go through our rate equation. All right, anyone wants Anyone wants to take on order of reaction? What is the order of reaction? Oh. Calicia Vassal has her hand raised.
The overall order of reaction is the sum of the powers of the reactant concentrations in the rate equation, whereas the order of reaction with respect to a specific reactant is the power of that reactant's concentration in the rate equation.
All right, any other definition? All right. I see in the chat, order of reaction is a measure of a reactant's mathematical influence on the overall rate of reaction.
Interesting.
Um,
And somebody has the order of reaction shows how the initial rate is affected by any one particular reactant.
okay, all right. All right, so we have some persons who are thinking and who seem to have started reviewing. We're keeping these in mind, and let us see how true these definitions are as we go through. All right. All right, so we're going to look at the rate equation. We spoke of the fact that the rate of your chemical reaction is basically defined as the change in concentration of a reactant or a product with time at a particular temperature. Now, the general rate equation that we have is that rate is equal to K, and K is your rate constant, and please note, this is a lowercase k or a common K, common letter, because capital K means something else. So you have to ensure that when you're writing this, that you write in the proper case. And I can tell you from years of experience, students lose marks because they use the incorrect case in writing these letters. So rate is equal to K times the concentration of reactant A raised to the power M times the concentration of reactant B raised to the power N. Now, rate has, of course, normally the units are moles per dm³ per second. That's usually what we utilize as the units of rate. In a particular set of data, you may find that something else is utilized, but if it's changing concentration, then of course you're going to have the units of concentration, and it's per a unit time, and our standard unit for time is seconds. That could also change depending on the reaction. So you need to ensure that you look at what is given to you in data that is supplied. Now for K, the units are calculated. There are no standard units for K. The units are calculated based on the data and the rate equation. Or square brackets denote concentration of your substance. And this again is also important. Square brackets is used for concentration. Parentheses are used for something totally different. So you need to ensure that you use the correct denotations in your equation. M and N are what we call the order of our reaction. So in general, if you're asked for the rate law or the rate equation, rate is equal to K times the concentration of your reactant raised to the power of its order times the concentration of your other reactant raised to its power, the power of its order. All right. All right. So what I find is that for us to be able to fully understand what is required in rates of reaction, it is best that we work with actual data. We don't just say, oh, first order or second order is direct proportionality. No, we're not going to work in a vacuum. So we're going to look at this data that is presented here, and your rate equation cannot be gotten, cannot be derived from the stoichiometric equation or from your balanced equation. You cannot derive your rate equation by just looking at the balanced equation. Your rate equation is determined based on experimental data. All right. All right, so this is information for the reaction between nitrogen monoxide and hydrogen. And I'm giving you just the basic data here. So 6 experiments were carried out, and you have the concentration of nitrogen monoxide in moles per dm cube and the concentration of hydrogen in moles per dm cube. The initial rate is given in moles per dm cube per second. So this is data that will be supplied to you. Now, based on this data, it says using the information from the previous table, deduce the rate equation and the value of the rate constant. All right. So what we need to deduce more than anything else here and now is the order of reaction with respect to each of our reactants. And we're going to look at how it is. So we want the value of M and N from this general rate equation. So we need to deduce the value for M and N for this rate equation. All right. So I'm going back now to my table. So we are trying to come up with the rate equation, and then we are going to also look at deducing the value for our rate constant. All right. Now, in our objectives, we spoke about zero order, first order, and second order reactions. And we want to look at what is zero order, what does zero order mean, what does first order mean, what does second order mean. All right. So for a zero order reaction, when we say a reaction is zero order, can anyone tell me what that means? Anyone remembers what zero order means? All right, to raise the hands.
It means that the concentration is constant. It is not affected.
The concentration is constant. That is what you said?
Yes, Miss. The rate of reaction is constant, or it is unaffected. The rate of reaction is unaffected.
All right, the rate of reaction is unaffected by what?
The change in the concentration.
Right. So it's not that the concentration is constant. For your zero order reaction, a change in concentration has no effect on the overall rate of the reaction. So it's not that the concentration remains constant. So for those of you with that misconception, it's not that the concentration remains constant. It is that changing the concentration does not affect the rate of the reaction. All right?
All right. There are some responses in the chat. You can let me know if you want them.
All right. Yes.
It says zero order means that the reactant has no effect on the rate of reaction. Somebody
Okay.
says no change. I'm sure they meant concentration doesn't change. There's no effect on the rate. The rate of reaction is not affected by concentration. The rate of reaction is not affected by the concentration of the reactant. And any changes in the concentration of the reactants have no effect on the rate of reaction.
Right. All right. So a few persons had the misconception that said the concentration doesn't change. So I would like for you to make a note, persons who had that as zero order. No, it is not that the concentration does not change. It is that a change in concentration has no effect on the rate of the reaction. So it is the rate of the reaction that does not change. All right? First order reaction. Someone explain to me, please, what is meant by a first order reaction?
Miss, in the first order reaction, the rate doubles as the concentration doubles.
All right. Okay, let me hear someone else. Partially right. No one else?
Okay.
So my question is.
There is Danae. Danae's answering. Go ahead, Danae.
Okay.
Then Crystal afterwards.
Other reaction is when the rate is directly proportional to the concentration. So if it is that you double the concentration, the rate would also double.
Okay. All right. Anyone else? You said someone else?
I thought Danae was answering. Danae, did you answer?
I think she's the one who answered.
Okay, yes.
I was saying that in a first order reaction, the rate of reaction increases or decreases proportionally with the concentration of the reactant.
Okay. All right. So it is a direct proportionality for your first order reaction. So the first person who said that if the rate doubles, the concentration doubles, the rate doubles. I was about to ask what happens if I triple the concentration. So when you are giving your definition or your explanation, make your explanation general so that it will fit all or as many possibilities, and do not limit it to saying if the rate doubles, if the concentration doubles, the rate doubles. Speak about the direct proportionality and then doubling the concentration and causing a doubling of the rate would be your example. Okay? Everyone understands that? All right, so that is first order. Second order, someone wants to tell me what happens in a second order reaction? Or when we say a reactant is second order?
Okay, there's a response in the chat. Second order implies that the rate of reaction increases with the square of the change in concentration.
All right, anyone else?
The second one is similar.
Mm-hmm.
Yes. Rate of reaction is directly proportional to the square of the concentration of the reactant. Yeah.
All right. Okay. So if I double my concentration, the square of 2 would be 4. So it means my rate quadruples. If I triple the concentration, the square of 3 is 9. So I get a 9-fold increase in the rate of the reaction. All right, so now that we have reviewed 0 order, first order, and second order, thank you so much for all the persons who answered, and I hope persons understand what 0 order, first order, and second order means. We're now going to look at how it is that we can use this information to derive our rate equation. So this is the data. A student would have, an experimental student, someone would have carried out these 6 experiments. And from this, you need to now come up with your rate equation. So rate is equal to K times the concentration of your nitrogen monoxide raised to its order of reaction. So we are going to first of all deduce the order of reaction with respect to nitrogen monoxide. How do we do this? If you're going to deduce the order with respect to a particular reactant, it means, therefore, that you have to ensure that this is the only reactant that is influencing the rate of reaction. And the only way that you can do that is to keep everything else, the concentration of everything else, constant. So I must keep the concentration, of my other reactant, hydrogen in this case, constant, to know that the only thing that is affecting the rate of reaction is the change in concentration of my nitrogen monoxide. Thumbs up if you agree with that. If you agree with that concept. Before we move on, you have, all right, so most persons agree with that concept. All right, so it means, therefore, I'm going to look at my data and I need to find which experiments my experimenter kept the hydrogen concentration constant and varied the concentration of my nitrogen monoxide. And when I look in the table, that would be experiments 4, 5, and 6. So whatever comparison I am doing, I am going to do the comparison using experiments 4, 5, and 6. Because any change in the rate of reaction in those 3 experiments will be solely due to the change in concentration of nitrogen monoxide. All right. So we have been speaking about doubling and tripling of concentration. So our base experiment is going to be experiment 4. So in experiment 4, the concentration is 1 times 10 to the minus 3 for nitrogen monoxide and 6 times 10 to the minus 3 for hydrogen. And my rate is 0.5 times 10 to the minus 3 moles per dm cube per second. Now, in order to deduce the order of the reaction, I have to change the concentration and see how this change in concentration affects the rate of the reaction. So I'm going to compare experiments 4 and 5. And I'm comparing experiments 4 and 5 because in experiment 5, I would have doubled the concentration of nitrogen monoxide. Now, how is it that I can mathematically show this? If I am comparing, I can set up a ratio because sometimes the questions are not just 1 mark, and sometimes they may ask showing using calculate, and if they calculate, they expect you to show how it is that you come up with your information. So I could decide that I am going to divide or set up the ratio between the concentration of experiment 5 and experiment 6 with respect to the concentration and then with respect to the rate. So experiment 5, the concentration would have been 2 times 10 to the minus 3, and that of experiment 4 is 1 times 10 to the minus 3. So the ratio of concentration, the ratio between the concentration of these two experiments would be 2 to 1. All right. Now, when I look at my rate, or I can divide my 2 times 10 to the minus 3 by 1 times 10 to the minus 3, and that would be equal to 2. When I compare the rate in experiment 4 is 0.5 times 10 to the minus 3. The rate in experiment 5 is 2 times 10 to the minus 3. When I divide 2 times 10 to the minus 3 by 0.5 times 10 to the minus 3, I am going to get 4 as my answer. So when I double the concentration of nitrogen monoxide, the rate of reaction quadruples or increases 4-folds. What does that tell me about the order of reaction with respect to nitrogen monoxide? All right, I see second order, second order, second order. All right, no order. All right, second order. Is there anyone who does not understand why it is second order or does not agree that it is second order? And please don't be shy. The purpose of today is to clear up misconceptions. So if you don't understand, I see a hand. Crystal, was that?
Yes, Miss. I was asking, Miss, when you look at experiment 5 and 6, Miss, the order, well, the rate of the order of reaction, Miss, it wouldn't be second order, Miss. So I was asking Miss if it's just like Miss, the entire reaction, it wouldn't just be a second order reaction. You just have to look at you have to look at the experiments as two, as in just look at 4 and 5, or if you're looking at 5 and 6.
You could look at 5 and 6 also, but 5 and 6 becomes a little bit more complicated. The easier way.
That's why I was asking, Miss. You wouldn't get a second order for this one, so Miss.
You wouldn't? Why wouldn't you get a second order? If I divide, all right, let's say I divide 3 times 10 to, let's do it. Do you have a calculator?
Yes, Miss.
All right. Divide 3 times 10 to the minus 3 by 2 times 10 to the minus 3. What do you get?
Miss, I get 3.01.
3 times 10 to the minus 3 divided by 2 times 10 to the minus 3. You said you're comparing 5 and 6.
Yes, Miss, and I said that I got 3.01. But Miss, let me do it again in the calculator.
No, ma'am, you should be getting 1.5. Isn't 3 times 10 to the minus 3 divided by 2 times 10 to the minus 3? Isn't that 1.5?
I'm not sure why I'm not getting that, Miss. Maybe something is, maybe I'm plugging in the information wrong.
It should be 1.5 that you're getting.
Unless some persons who got 1.5 in the chat.
Right. Oh, somebody say use exponent. Oh yes, that's what you're doing. If you use your EXP button on your calculator to put in the times 10 to the minus 3.
Yes,
you
Miss.
don't put times 10 to the minus 3. You use EXP. If your calculator, I think is Casio, it has the EXP button. All right, so it should be 1.5. All right, now divide 4.5 by times 10 to the minus 3 by 2 times 10 to the minus 3. I beg your pardon?
Miss, can you repeat that, please?
We're now dividing the rates. So it's 4.5 times 10 to the minus 3 divided by 2 times 10 to the minus 3.
So I get 2.25.
All right. Now, what is the square root of 2.25?
Is that about 5 right there?
No, the square root, not the square. Square root of 2.25.
Oh, 1.25. Is that's the 1.5 that I got?
Right. So it means therefore it's second order.
Oh.
Because remember what we said. It is when it is second order because whatever the factor is that you change your concentration by, your rate is that factor raised to the power 2 or squared. So if when I divide through my concentrations, I get 1.5. And when I divide through my rates, I am now getting, you said 2.25. The relationship between 1.5 and 2.25 is that 1.5 squared is equivalent to 2.25. So it's still second order.
All right.
Any clearer? Right. So no, the relationship remains that when whatever factor you change your concentration by, your rate is changed by the square of that factor. But generally, we like to do nice, easy comparison that you can basically do the calculations in your head. So I would tell my students, you will compare experiments 4 and 5, which is doubling, or you compare experiments 4 and 6, which is tripling. So it is easy for you to say, oh, the rate quadrupled or the rate increased 9-folds. All right. Anyone else who is confused before I move on to our second reactant? Anyone else with a question? This is where you ask your questions. No questions? We're all fine? All right. So far we have rate is equal to K times the concentration, square bracket, NO, raised to the power 2. So far we have that for our rate equation. Now we need to find out what is the order of reaction with respect to hydrogen. So this time we need to keep the concentration of nitrogen monoxide constant, and that is what is done in experiments 1, 2, and 3, and change the concentration of the hydrogen. I see a question. So we divide the concentrations first, then the rates, and then divide the rate by concentration. Yes, you could do that to get the factor. That's a question. Right. Yes, you can do that. And it should give you the factor of 2. All right. So experiments 1, 2, and 3, nitrogen monoxide concentration is constant and the hydrogen concentration is being changed. All right. So we can again, here we're going to compare experiment 1 and 2. When I divide 2 times 10 to the minus 3 by 1 times 10 to the minus 3, I get 2 as my answer. When I divide 6 times 10 to the minus 3 by 3 times 10 to the minus 3, we're looking at the rates now, I also get 2. If I divide the factor of the concentration, which is 2, by the factor of the rate, which is 2, I get 1, which gives, who is lost? Remain?
Yeah, somebody says,
yes, I just saw it.
Do you want to use a whiteboard or something? Probably he wants to see it worked out.
All right, let Remain open his mic and tell me where I lost him. If I lost him at the very beginning, when I was explaining, answering Kira Rose, or I lost him for hydrogen. Okay.
Remain, can you raise your hand so we can find you?
Right, and you can tell me where I lost you.
I'm not hearing from Remain. Remain? Okay, Remain, go ahead. Oh, his mic's not working. Oh, all right, well, you. All right.
From the very beginning?
Let me see. Oh, somebody's asking you to go from the very beginning?
No, Romain says that he's lost from the very beginning.
Oh, okay. But if you could probably break or
all right, let me
oh, somebody's saying if you could move your cursor so we can see what you're referring to if you opt not to use the whiteboard.
Oh, so the cursor was
no, man, I think they want you to where you're indicating where doubles and where triples and so on.
oh, right
could,
here. Okay.
Right, indicate on
okay.
the thing, right? Or
all right.
Or use the whiteboard, right?
All right, let me. This device that I'm using is not touch screen, so
okay.
Let me see. All right. Let me see if I can. Just give me a second. Can you still see?
Yes, I'm seeing.
Right. So, all right. Let me use the PowerPoint slide. So if we are, and let's see if we can catch up with Romain. So we are trying to find M, the value of M in this equation. So to find M, oops, sorry. I know what went wrong. Let's go home. Take out the superscript, come back. Sorry about that. So to find
someone is suggesting that you can use the laser feature to draw the slide. So.
All right. All right. So to find M, what we're going to do, we're going to compare experiments 4 and 5. All right. That is to find M. All right. So experiment, concentration. So we're going to look at the concentration first. And experiment 4, the concentration is 1 times 10 to the minus 3. All right. Don't have the time to subscript and superscript, so just keep that in mind. Experiment 5, the concentration would have been doubled. So it was 2 times 10 to the minus 3. All right. If we want to find the factor by which our increase is, can't spell, finding the factor by which we increase, then we would say 2 times 10 to the minus 3 divided by 1 times 10 to the minus 3. And this would give us a factor of 2. So we have doubled our concentration. We will then look at rate, and we're looking at the rate as given in the data table. And for experiment 4, if I'm remembering, correctly, it was 0.5.
Yes, 0.5.
Times 10 to the minus 3. And for experiment experiment 5, it was 2.
Yes, 2.
Times
yes,
10
2.
to the minus 3. All right. And our factor here, oops, can't spell. Our factor here is going to be calculated by saying 2 times 10 to the minus 3 divided by 0.5 times 10 to the minus 3. And here, that would be equal to 4. All right? And therefore, the order is going to be 4 divided by 2, which is equal to 2, which gives me my second order. Romain, is that any clearer? Romain?
Yeah, I think you would have to type in the chat, Romain, if it's clearer. He said yes.
Okay, so the yes. All right. You are welcome. That is why we're here. All right. So these are the same steps that we're now going to. I know persons are telling me about laser feature and all of this. I am not that tech savvy. I can help myself. I can help myself if I have time to help myself and to learn the feature. But unfortunately, it's not under all. I can help myself.
Okay.
All right.
Remember to mute your mic, students, if your mic is open.
Yes. All right. So we would have just done nitrogen oxide. Let me just put it right here. So that we know. This is a new slide. So nitrogen oxide, order of reaction. Ooh.
I guess if you use the cursor and indicate the ones for the hydrogen, they could work it out now.
Okay, all right. So we're jumping back to slide number 7. Let me see if I go back into my slideshow from current slide. Right, nice and big so that I can see it also. So nitrogen. So my nitrogen, for hydrogen, we are going to be looking at, for hydrogen, we're going to be looking at experiments, comparing experiments 1 and 2. So the concentration of hydrogen in this case is 1 times 10 to the minus 3 for the first experiment. And then for the second experiment, it is 2 times 10 to the minus 3. Everyone seeing that?
Yes, yes.
So everybody is seeing that? All right, so now we are going to divide, just like we did for nitrogen oxide. We are going to divide 2 times 10 to the minus 3, experiment number 2, by 1 times 10 to the minus 3, which is experiment number 1. And that should be equal to 2. So our factor should be 2. Then we're going to take the rate. The rate for experiment 2 is 6 times 10 to the minus 3. We're going to divide that by the rate for experiment 1, which is 3 times 10 to the minus 3. And that should also give us a factor of 2. So if I divide the 2 from the rate by the 2 from the concentration, I get a value of 1. I see my chat is lighting up. Is it that I've lost persons?
No, they were asking about the recording. Sorry.
Okay, okay.
Okay.
I thought I'd lost them again.
No.
I thought I lost them again. All right. So that would give me. All right. So could you look in the change in the rate? No, you can't just look at the change in rate in isolation, because remember, you are changing the concentration, which causes the rate to change. So you need to know, how have I changed the concentration to lead to what sort of change in the rate? So if I double the concentration and then my rate doubles, then that's a direct proportionality. But if I triple the concentration and the rate triples, we also know that that is a direct proportionality. So you can't just look at the rate in isolation, because the two are directly related to each other. Does that answer your question? Or maybe I misinterpreted your question, so you can explain what it is that you meant.
All right, she said it did. It clarified.
Okay. So you have to look at the two aspects, because one causes the other. So I'm not going to get a change in rate without a change in concentration. Okay? Now for our zero order, no matter, as you stated, no matter what it is that we do with the concentration, the rate is not going to be affected by any change in the concentration of a reactant that is zero order. So for this particular reaction, the rate law or the rate equation is going to be rate is equal to the concentration of nitrogen oxide raised to the power 2 times the concentration of hydrogen, because the 1 is understood. Everybody understands? Thumbs up if you get our rate law for this particular reaction that we're looking at.
Okay, someone wants you to repeat the rate equation.
Oh, the rate equation. All right, let me, because I'm going to make reference to it. All right, so let me write it here based on what we just worked out, rate. Oops. So I'm going to write it down, because I'm going to give you something to do based on this. So rate is going to be equal to K. Notice it's a common K, square bracket, and O raised to the power 2 square bracket, H2. All right. So that is our rate equation. All right. And we just worked that out. We derived that from our data that was supplied based on the experiments. Remember, you cannot look at, notice I did not even write the balance equation because I don't want the confusion. Normally you are given a balance equation, but I don't want you to think, I did not want you to think that you can look at your balance equation and come up with your rate equation. No, rate equation must be deduced from experimental data. Your rate equation must be deduced from experimental data.
Someone is asking about putting the 1 at the hydrogen.
The 1 is understood. It's like, it's an index. Remember, anything raised to the power 1 is itself. All right? Sorry, somebody seemed to be confused. What did you, Brianna said something and someone was answering her. What did
no, it was cleared up. It was cleared up.
Okay, okay. All right. So this is my rate equation now. And the second, so we would have answered the first part of this question, which says that you're to deduce the rate equation. The second part said, and the value of the rate constant. So you're going to calculate, I'm going back to my data table. This is my rate equation. You are going to calculate for me. And when they ask you to deduce the value of your rate constant, you must put the units. Generally, this is worth 2 marks. You lose a mark if you don't have any units there. So their value will have 2 marks. If you don't have the units, you lose a mark. If you only have a numerical value, you're going to lose a mark. And if by any chance you make a mistake and the numerical value is wrong, it means that you lose both marks. All right, so to calculate K, all you need to do is to take the data from any one. You're going to take the data from any one of your experiments and simply insert this data into your equation. So I'm going to ask you to quickly choose any one, experiment 1 to 6. And I'm going to ask you, Alton, I'm going to ask you to calculate the value of K for me, please.
So we have a first answer. We'll wait on a few more.
Roberts, you're not playing fair. Roberts, you want me to give up your secret? Same question? Yes. So it's values from here. Any experiment, just one of the experiments you're using. Curtis, I would expect that you got the same thing as Alton. And Jeremy, I don't want you to answer either.
I see. It seems if they are known.
And they are my students.
Okay, all right, all right.
And they know exactly why I said that. All right, so I'm giving the others another 30 seconds. All right, is there anyone who did not get 8.333 time? You're unsure of the units, all right. Someone said that they got the same numerical value, but they're unsure of the units. Sorry, 8333.3333.33. All right, so no matter which of the experiments, because if you use experiment 1, you're going to get the same value as if you used the data from experiment 3 or the data from experiment 6. Because K is your constant for this particular reaction at this temperature. All right, so the units. Let us work out the units. Oops, wrong place. Let me go back. All right. So this is where I'm at. And I'm going to my blank. All right. Sorry about that. K is going to be equal to, no, let me change back my K, common K is going to be equal to rate divided by concentration of NO squared times the concentration of hydrogen. All right, oops, sorry, wrong brackets. All right, so to work out our units, we're going to work our units just like we would work any other mathematical value. So I tell my students, when you're doing calculations, here you write your numerical value and you can write immediately beside it the equation for the units. So my units, mole per dm cube, second to the minus 1. All right, so that's for my rate. And then I am going to have all of that is divided by mole dm minus 3, sorry. Wrong place. And this is going to be squared. And this is times mole dm to the negative 3. All right. So I have mole per dm cube per second divided by mole per dm cube squared times mole per dm cube. So technically, I can strike out my mole per dm cube and my mole per dm cube. So this would leave me with, wrong place, backspace, go back, enter. So this is going to leave me with seconds to the minus 1 divided by mole squared dm to the minus 6. But remember, with your index, with indices, if you divide, then it is for your indices, when you divide, you basically subtract your index. So your units now become
Do you want to put the seconds last?
I'm going to change it. It's just
Okay,
I just
okay.
want to show them the order, how it is. All right. And your DM now becomes positive 6 because it's minus minus. So what I had on top remains. So second to the minus 1. This is now dividing, so it is a negative, so it's mole minus 2, and minus minus 6 becomes a positive 6. So then my units, mole, sorry, wrong, dm to the 6th power mole minus 2 second minus 1. I see the chat is lighting up. Who have I lost? Just give me a second. Let me make sure that these look like what they're supposed to look like, and then I will answer all of your questions.
Okay, so you have lost a few with the units. You can just put them
Yes, I'm going to go over it again. This is where the math comes in. All right. This is where the math comes in. All right, so let's go again. So the equation for K is equal to the rate divided by, and we're taking this directly from our rate equation. Remember, we said that rate is equal to K times the concentration of nitrogen monoxide squared times the concentration of hydrogen. That's our rate law or rate equation for the reaction. All right? So that is, now when we rearrange and make K the subject of the formula, we get rate, K is equal to rate divided by the concentration of nitrogen monoxide squared times the concentration of hydrogen. All right, everybody's fine with changing the subject of the formula. Now, what we are now looking at are the units that are associated with each of these quantities. So each of these quantities come with their own units. The units based on the information given in the table, the units for rates is mole per dm cube per second. Let me change this. Maybe that is part of the confusion, and put a minus right here so that you will see it. So the units for rates is mole per dm cube per second. Those are the units. If I square the concentration, the unit for concentration also squares. So my mole per dm cube for nitrogen Your mole per dm cube for nitrogen monoxide is now mole per dm cube squared, not 2. Let me superscript this so that you can see it better, and maybe that will also assist. So mole per dm cube squared. The unit for hydrogen concentration is mole per dm cube. No, so technically what I have is mole per dm cube per second divided by mole cube dm to the minus 9. That's technically what I have, because I have mole per dm cube squared times mole per dm cube, which is the same as cubing it. But I have mole per dm cube here up top. So if I cancel this, I can't even, I want to strike through. Let me see if I can get a strike through. So I am all right. Let's see if we. So that all right. So what I'm left with is my per second and mole per dm cube squared, which is the same as mole squared dm to the minus 6. All right, I see my chat is lighting up. Let's see. All right. Is it any clearer? The person who was confused. Let me go back to the chat.
I think Denny was lost. Denny, please indicate if you're understanding now. Somebody's asking, why is it 6 and not 9?
For your indices, you multiply your indices when you,
or you add.
Sorry. No, it's a squaring it. So it is, so when you are squaring, when it's a quotient, you are going to multiply them. If you multiply two values, you add them, but in this case, like how we are squaring, then the minus 3 is multiplied by the 2. Laws of indices. I forget, I'm trying to remember the mathematical law, how it is, but I have not taught math in so long that I can't remember the exact law. So if you divide, you minus. If you are multiplying, you add. If you are squaring, cubing, anything like that, then you multiply the two indices together. All right. All right. Right. So persons, my mathematical students are answering for me. Thank you very much. All right. Is there any other questions with respect to the units?
Not at this time.
All right.
You may want to speed to your questions based on the time.
Based on the time, yes.
Right.
All right. What I can do, Dr. Taylor.
Yeah.
I can probably send the PowerPoint.
Okay.
And I don't know if for persons who may have issues and just need to go through.
Okay, no problem, no problem.
All right.
Okay, there's a raised hand.
Yeah. The PowerPoint has the major information. Yes, go ahead.
Miss, I was just asking, please, Miss, before the meeting, if you could look at the Boltzmann distribution, please, because I think I'm having a challenge with that.
Oh, Boltzmann, yeah, I was looking at it and saying maybe I need to do that.
Yes, Miss.
The Boltzmann distribution. All right. Let me quickly go through the factors. It looks as if I'm going to, so long as persons are willing, I will spend just a little more time beyond the 4:30. And since that's a request, Dr. Taylor, you have a problem with that?
Not a problem.
All right, because the student asked specifically for that, so I will go through that. All right, let's go back. All right, so the three factors that are of importance in your syllabus with respect to affecting the rate of a chemical reaction are concentration, temperature, and catalyst. Now, for concentration in general, as concentration increases, the rate generally increases. Why is it that I say in general and I don't just say every single time? We just spoke about it. One person. Let's see if you make. If you have made that, what type of under what conditions will the concentration not cause an increase in the rate of the reaction? Zero order. Thank you, Danae. So that is why we say in general, because if you have a reactant that is zero order, then it will not change the rate of the reaction. Also, generally, increase in temperature causes the rate of the reaction to increase. And of course, the presence of a catalyst will alter the rate of a chemical reaction, generally causing it to increase, but you can also have inhibitors, which are special catalysts, which slows down the rate of reaction. And chemical engineers especially find this useful if you have an explosive reaction that you need to slow down. It's an important one, but you can't use it at the rate that you have. All right, so here we have what is called Boltzmann distribution curve. And what Boltzmann distribution curve basically tells us is the number of particles within a reaction mixture that will have a particular energy. And for a reaction to take place, we need to understand that two things of importance must take place. The reactant particles must collide in the correct orientation. So they must have a certain orientation. And these particles must have a minimum amount of energy, which is called your activation energy. So Boltzmann distribution curve gives you the general distribution of energy of particles within a reaction mixture. Now here, our activation energy is denoted by this dotted line, and the blue area shows the proportion of particles in the sample that have enough energy to react. So the rest of these particles do not have enough energy to react. They do not have the minimum amount of energy, which is your activation energy. All right? All right. Now, Boltzmann distribution curve is important for two of your factors. That is temperature and catalyst, presence of a catalyst. Now, for temperature, the activation energy is the same. So the activation energy does not move. What happens is that as you increase the temperature of a sample of particles, remember they're going to absorb heat energy, and so their kinetic energy, the energy with which they move, will increase. So my blue graph shows at normal temperature or whatever temperature you're carrying out your reaction at, and my red graph shows the reaction, the distribution of particles at a higher temperature. Now notice the blue section here indicates the number of particles, and if I carry across, just a small fraction of particles have the minimum energy to react. When I increase my temperature, the number of particles that now have that minimum energy will increase. So it now increases. So as the temperature increases, the number of particles with the minimum amount of energy to react will increase. So more particles will have the minimum energy and collide in the correct orientation in order to react, and therefore the rate of the reaction increases. Any question? Person who asked for that, that's the first factor. All right, explain again. Colleen, can you open your mic and tell me exactly what it is that you don't understand, so that I know what I need to emphasize? Mic not working?
I want you to start from the first graph.
From the first, okay. So let's go back. That's what I wanted to know, if it was the temperature or it's, all right. So this is called your Boltzmann distribution curve, and it tells you how energy is distributed, energy of particles is distributed within a sample of particles. So if I have hydrogen gas sitting down in the lab in a cylinder, most of those particles will not have the minimum energy required to react. Most of them will be in this white area. All right. Some of the particles, only those that have energy above this energy here, will be able to react spontaneously. All right. And notice you have kinetic energy is on the x-axis, and the number of particles with the kinetic energy is on the y-axis. So this is the distribution curve. All right, any questions on this curve before I move to temperature? Any questions? No? All right, so everybody, person who said start from the first graph, you understand what the graph is telling you? All right, temperature now. So it's the same curve, just a little more compact. So it's the same curve, but here we're looking at Right, the particles that, because notice, kinetic energy is on the x-axis. And of course, we're increasing from 0. So the particles that are down here have the most energy. All right? All right. So here now we're looking at what happens when we increase the temperature of a sample of a reactant. So in blue for this, we have our normal distribution curve at whatever the lower temperature is. If it's room temperature, let's say it's room temperature. Then I'm going to increase the temperature, say by 10 degrees, all right? When I increase the temperature of my sample by applying some heat to it, more particles are now going to have that minimum energy because I get a shift in my curve. Notice my curve has shifted, and I'm going to get more particles having this minimum energy or activation energy. So for my blue graph, if I take from my blue graph and I extrapolate to my y-axis, I would get a value somewhere down here. When I increase my temperature, and that would tell me, let's say that is a value of 5. I'm just just giving you some numbers so that you can make the connection. When I increase my temperature now, when I've increased my temperature, my value goes up to say 10. So that tells me that twice as many particles now have that minimum energy. So if twice as many particles have the minimum energy required to react, it means that the rate of my reaction is going to increase because more particles have this minimum energy that is required. Any questions on that?
No questions at this time.
Okay, raised hand. I see a raised hand.
Okay, give me a sec. Go ahead.
Saying for the higher temperature, based on the graph, we have more particles with the activation.
I'm getting a little disturbance. I'm not hearing you. I don't know if it's wind or something. Go again, please. Yes, I'm hearing you now.
Miss, I was saying that for the curve in which have the higher temperature, miss, is it that the red, miss, the part that is shaded red, is it has more particles than the part that is shaded blue, right?
Yes, because when you carry it, okay, for the red, it is all of the original particles plus the additional that would now have the energy.
Okay.
Right, so it's everything, but they're just comparing to show you that this was the amount, this was a number of particles that had the minimum energy, and now you have this additional number of particles. All right,
Okay,
so it's everything.
You have more particles getting kinetic energy, and as a result, you have a lot more particles being, of the activation energy are greater than it, so that you have more particles on that side of the curve.
Yes.
I understand.
Okay. All right. Catalyst. Now, our catalyst, as we know, is a substance that alters the rate of a chemical reaction. Now, catalysts work by providing an alternative pathway for the reaction with a lower activation energy. So let's go back to, let's look again, Boltzmann distribution curve. This line here that my cursor is on is the original activation energy for my uncatalyzed reaction. When the catalyst is, when you add your catalyst, the activation energy is lowered. So the value for that activation energy is lower. And therefore, you have additional particles that now have that minimum amount of energy required in order to react. So uncatalyzed, only the particles in this gray area would have enough energy. For your catalyzed, everything in the red and the gray area now have the minimum energy for the reaction to take place. Any questions? Any questions?
Not seeing any at the moment.
Not seeing any at the moment. All right. So, I see something in the chat.
Yeah, about going it over. Oh, I probably don't want you to hover over it again or something.
Okay, okay. Miss, okay. So here, this is the original activation energy. These are the particles in the gray area, the number of particles that have that minimum energy for the reaction to take place. When the catalyst is added, the activation energy is lowered, and these additional particles in the red area now have enough energy to react. So the total number of particles that have the minimum energy would be the particles in the red area plus the particles in the gray area. All right. Any clearer? The person who...
Yes, she says okay.
Okay, the person who specifically asked for Boltzmann distribution to be explained. Are you clear now? That person, I need to say, yes, they're clear. Raise hand.
It was me, Miss. So far this, for the catalyst one, Miss, you don't draw two curves. Miss,
No, it's one. So temperature, it's two curves. Catalyst is one.
All right, Miss. Thank you so much, Miss. Miss, I was the one that asked for you to explain.
Oh, you're the one who asked? Okay, so you're okay now.
Yes, Miss. Thank you.
You're welcome. All right. All right, let me jump to questions and see if we can. I'm going to stop sharing so that I can share my my question screen. Give me a second, please. Did I just? So I am sharing. If I could find. No. Here.
What?
All right. Are you seeing the question?
Yes.
All right. Beautiful. All right. I am Give me a second. Let me show as much of this question as possible.
I think some person start answering the question.
All right. So I'm going to ask you, let us, I see that some persons are answering the questions. So let us see if we can go through this very quickly and see how far we get. All right, so this is 2018, if I remember correctly, 2018. Question number 2, part A. Now, questions like part A, please remember, well, this is the CAPE level. At the CSEC level, most of you would not have done a paper 2, but last year you would not have done paper 2. But normally at the CSEC level, most of the questions are recall and some of them are use of knowledge, application. Here at the CAPE level, most of the questions are application and a few recall, straight recall. Also, because you now do a 30-mark question per module, what you will find in those 30 marks is that you get your data analysis or your experimental based question. Now, the experimental based aspect of the question sometimes is as much as 10 marks out of the 30. All right, so you need to keep in mind that you must be able to speak about experiments, give instructions as to how to carry out experiments, and so on for these questions. All right, so state 2 factors which affect the rate of a reaction. And I see persons placed in the chat, different factors. So any 2 of the following would have given you 2 marks. Surface area, concentration of reactants, temperature of reactants, catalyst, light. All right. Part B, the data in table 1 were obtained for the reaction between hydrogen. we just did this. And I didn't get it from here. I didn't even realize the data in table 1 were obtained for the reaction between hydrogen and nitrogen oxide at 800 degrees Celsius. And see, they gave you the balanced equation. And the reason why they're giving you the balanced equation, they want to see whether or not you understand that your rate equation must be deduced. All right, must be deduced from the data and not from the balanced equation. All right, so here they say define the reaction rate in terms of the production of nitrogen. Who wants to take that on? All right, let me see in the chat. Oh.
All right, there were responses about the factors. I don't see anything else about
Rate of reaction. Somebody
Oh,
define
yes,
the rate.
reaction rate. Yes, is a decrease in nitrogen monoxide and consequent increase in nitrogen with respect to time. I'm sure they meant hydrogen with respect to time.
Okay. All right. So you could have written the equation, change in concentration of nitrogen, because they asked for it in terms of the production of nitrogen. So change in concentration of nitrogen divided by time taken. And you would have got, if you wrote that equation, you would have gotten your 2 marks, or you could have defined it as change in the amount or concentration of nitrogen per unit time. 1 mark for change in concentration of nitrogen, 1 mark for time taken or per unit time. All right. So that's how you would have gotten your 2 marks. My computer is slowing down. I'm sorry about that. Don't know what the issue is. Let me make sure that, okay. All right. And we would have done this here from the data. Determine the order of the reaction with respect to hydrogen and then nitrogen monoxide. Now notice they gave you space here. So they're expecting you not just to write first or second order, but they're expecting you to show them something. All right, so we already deduced that with respect to hydrogen, it is first order. With respect to nitrogen monoxide, it is second order. We did this earlier. Chat is lighting up. All right. And it says write the rate law for the reaction. Remember, the rate law is the same as the rate equation. So we just did the rate law, and we said rate is equal to K times the concentration of nitrogen monoxide square times the concentration of hydrogen. Then they said calculate the value of the rate constant K, stating the appropriate units. So we would have done that also. You see this 3 marks. So for your 3 marks, you're getting 1 mark for the expression, that is K is equal to whichever values you have taken out of your table. So if we are looking at, say, experiment number 2, then it would have been 6 times 10 to the minus 3 divided by 6 times 10 to the minus 3 squared times 2 times 10 to the minus 3. So once you write that expression, you get a mark. Then you get a mark for your value of 8.33 times 10 to the 4. That's where the second mark comes in. And then the third mark comes in for the units. Mole to the minus 2, dm6 per second, s to the minus 1. All right, chat. If you need to state the experiment, not necessarily, but it makes it easier when the examiner is marking to see where you took your values from. But there is no real penalty. It just makes it easier. All right, C, suggest another experimental. Why does this look as if? Okay, suggest another experimental technique which would be suitable to investigate the rate of reaction between hydrogen and nitrogen oxide. All right, so I'm getting, so the reactant and products are all gases. So the measurement of pressure at suitable time intervals would be appropriate. So don't just say gas measurement method. Be specific, measurement of the pressure of the gases. All right. All right, the investigation of the effect of concentration on the rate of reaction between aqueous bromine and methanoic acid in large excess is catalyzed by acid. Outline the experimental steps required. And that is 4 marks. No, it's not necessarily the volume, it is, sorry. Let me scroll to the question. Sorry about that. It's the pressure that is of importance. No one answering? It's 4 marks, so I need the steps. Can I get the steps, please?
All right, so I was seeing some responses here. Oh no, not yet. Not with the steps. Are they to be answering about steps, experimental steps? Because I'm not seeing any responses for that.
All right, let me go through, seeing that they're not, and we're a little strapped for time. All right, so the concentration of the methanoic acid is constant, can be considered constant because the question says it's in large excess. All right, so the concentration of the methanoic acid is constant due to the amount being in large excess. The bromine, aqueous bromine, is reddish brown, and the concentration of the bromine decreases or falls during the course of the reaction. The intensity of the reddish brown color can be followed by a colorimeter at suitable time intervals. So you would decide on the time intervals. A calibration curve of known bromine concentration against the colorimeter readings would be plotted and the bromine concentration deduced. The concentration of bromine is then plotted against time. The tangent is drawn to the curve at given times to obtain the reaction rate. The reaction rate is then plotted against the concentration of bromine. Now, this has 7 steps. So if you gave 6 to 7 steps, you get all 4 marks. 4 to 5 steps out of the steps that were just given, you get 3 marks. 2 to 3 steps, you get 2 marks. And 1 step, you get 1 mark. All right. Yes, raise hand. Hands are raised.
Yes, miss. Question. What if you condense the steps into like 1 step? As long as you have it, you'd still get full marks?
So long as you have all of these components.
Okay, okay.
So if you write a paragraph, so long as the examiner can identify all of these steps, you get your marks. All right, go over again. All right. So the assumption that you need to mention is that the concentration of the methanoic acid is constant due to the amount being in large excess. So the methanoic acid is not going to affect your rate because it's not going to be monitored because it's in large excess. So the question is out of 4 marks. So so that needs to be stated. Now the aqueous bromine is reddish brown, and we know that. Based on this equation that they've given us, the concentration of the aqueous bromine is going to decrease during the course of the reaction. Now, because the aqueous bromine is colored, the intensity of the reddish brown color can be followed by a colorimeter at suitable time intervals. You are going to produce a calibration curve. So you take known concentrations of aqueous bromine and you're going to put them in the colorimeter and get those readings. So a calibration curve of known bromine concentration against the colorimeter readings will be plotted and the bromine concentration deduced. So you're taking your known, plot your graph, You now take your experiment, run your experiment, and you take color readings at different time intervals. Those you're going to find, by those you're going to then find on your calibration curve, so that you get your you can deduce your concentration. The concentration of bromine is then plotted against time. A tangent is then drawn to the curve at the given times to obtain the reaction rate, and the reaction rate is plotted against the bromine concentration. So that is one method. All right. For the second method, which is a 5-step method, shorter, easier, but the carbon dioxide gas, because carbon dioxide gas is produced, the volume of carbon dioxide is measured at time intervals. The volume of carbon dioxide is plotted against time. The tangent is drawn to the curve to determine the reaction rate. And then the reaction rate is plotted against the volume of carbon dioxide. So that's the easier method. So the second method, carbon dioxide gas is produced. The volume of carbon dioxide is measured at time intervals. The volume of carbon dioxide is plotted against time. The tangent is drawn to the curve to determine the reaction rate. The reaction rate is plotted against volume of carbon dioxide. Now, if you have all 5 steps, you get 4 marks. If you have 4 steps, you get 3 marks. If you have 3 steps, you get 2 marks. If you have 1 to 2 steps, you get a mark. All right. Yes, Crystal?
Miss, I'm always asking if you could please repeat the one for carbon dioxide, miss, as I was writing it.
Okay. So for carbon dioxide, you must make the statement that carbon dioxide gas is produced. Then the volume of carbon dioxide is measured at time intervals. The volume of carbon dioxide is plotted against time. The tangent is drawn to the curve to determine reaction rate. The reaction rate is plotted against the volume of carbon dioxide. And remember, if you did not get all of the steps, the recording, Dr. Taylor, the recording will be on YouTube, right? They can simply go and search and you can go back through. What did I just do? Oh. Let's see what I did. I did something. Where am I? Oh, here.
It is being streamed live on YouTube, so it is already on YouTube and you can always check it.
All right. Let's see if we can quickly go through another question. We're in overtime. All right. Let me find this one. Yes, I think. All right. Explain each of the following terms. Explain each of the following terms. Rate law. Responding persons started responding. Let me check the chat. Rate law. Yes, Crystal.
Miss, is the rate law the relationship that exists between the concentration of reactants and the rate of reaction? Is it that?
All right. Anybody else? I'll soon tell you if that is it. Anybody else?
I have something similar in the chat, relationship between the concentration of reactants and the rate of reaction.
All right. All right. So the rate law, the expression or equation that gives the relation between the rate of reaction and the concentration of individual reactants. All right. Or you could have simply written rate is equal to K times concentration of a substance, X, Y, whatever, raised to the power M or N or something like that. All right. So you can use one reactant or you could use two. All right. Order of reaction. Order of reaction. All right, so the order of reaction with respect to a reactant is the power to which the concentration of the reactant is raised. All right. Is that a question or order of the order of reaction with respect to a reactant, and you need to put that in with respect to a reactant, because remember, you can have the overall order of a reaction. So the order of reaction with respect to a reactant is the power to which the concentration of the reactant is raised. All right. Parts B1 to B3 refer to the following reaction, AX plus BY to give products. Write an expression for the rate law.
You can post your responses in the chat, students.
Or if you can
okay,
tell
we have one here. Rate is
Okay.
equal to K, Y to the A, and Y to the B. Really? Or they probably made a mistake and didn't put the X. All right. Guess it should have been X to the A and Y to the B. Or somebody says rate is equal to K, X to the A, Y to the B, concentration of Y to the B. Rate is equal to, yes, same thing.
All right. Guess what? If you use A or B, you're not going to get your marks. Because if you use A or B, you're telling the examiner that you're getting your rate equation from your balanced equation or from your stoichiometric equation. And we already stated that you cannot get your rate law or your rate equation from your balanced equation. So you must write, you need to use any other letters except for A and B. So your rate law, you could have written rate is equal to the concentration of X raised to the power C times the concentration of Y raised to the power D. Or rate is equal to K times the concentration of X raised to the power M times the concentration of Y raised to the power N. You cannot, if your powers are A and B, then you are not going to get the 2 marks. You are not going to get the 2 marks. So if you had rate is equal to K times the concentration raised to the power A, concentration of X raised to the power A times the concentration of Y raised to the power B, or vice versa with those powers, you would only get 1 mark for having the K correct. Yes, Crystal? The marks will not be given, Colleen, because A and B are given as coefficients as part of your equation. And your rate law cannot be deduced from your balanced equation. It must be deduced from experimental data. So if you use back these coefficients, A and B, what you're saying is that you have derived your rate law from this balanced equation. And that is not true. Any clearer, Colleen? Any letters, in this case, any letters can be used except A and B. Any letters could be used for this particular one, except A and B, because A and B are utilized in the balanced equation. Yes, Crystal?
Miss, Miss, I understand why you said that, Miss, but I got this question at one point, Miss, where the reactant, Miss, you had a coefficient in front of it. Miss, is it that when you're going to do the rate equation, Miss, would you raise the reactant to the coefficient in which is in
No,
front of it?
that's equilibrium. That's chemical equilibrium.
So, Miss, you would disregard the coefficient in front
Right,
of it?
because you have to deduce the order of reaction based on the experimental data.
Yes, Miss, that is the order, Miss, but I'm asking about like the rate, as in like the rate equation, Miss, if you wouldn't put the coefficient like
No,
as this.
no,
It's still O.
no. The coefficient in the balanced equation does not affect the rate equation.
So we shouldn't use it at all.
Go again?
I was saying that we shouldn't use it at all. We should just
No,
disregard it.
no, not for rates.
All right, miss.
Not to come up with the rate equation in any relation to the rate equation. How you get your rate equation, and that is why in the PowerPoint I deliberately did not utilize, did not give you the balance equation to show you that you have no need for the balance equation in order to come up with your rate equation.
All right, miss, thank you.
Okay. Write an expression for the overall order of reaction. What's the overall order of reaction?
Okay, we're getting m plus n.
Right. So whatever letters you used for the order, it would be the sum of them. All right, the overall order of this reaction was found to follow second order kinetics. Deduce the units of the rate constant for the reaction.
Okay, here's a response. dm cubed per mole per second.
That's correct. (2017). All right, so dm cubed per mole per second, because if it's second order, then we know that our concentration units are going to be squared. So the same way that I went through the deduction of the units in the PowerPoint, that is how you would do it. And so you would get mole per dm cubed per second divided by mole squared dm to the -6. Of course, when you cancel, you have mole to the -1 dm cubed per second. All right. We did not get a chance to look at reaction mechanism in the PowerPoint, but we're going to do this question. The decomposition of gaseous nitrogen 5 oxide exhibits first order kinetics and is represented by the equation, and they give the equation. A proposed mechanism for the reaction is made up of the following steps. W and Z are intermediates. Use the information relating to the kinetics of the reaction to write the equation representing the rate determining step, giving a reason for your response. All right, so NO2, O5 to give W plus O2. What's your reason?
They want you to scroll up so they can see the entire equation, entire question, sorry.
What's your reason?
So Stuart says N2O5 is the only reagent.
Right, and so it would have to be a part of the rate determining step. All right. So for this particular question, they wanted you to choose from the questions given the one that you would designate the rate determining step. All right. The next. Oops, sorry, went too far. All right. For the second part of this, they said data for the decomposition of nitrogen 5 oxide at 333 Kelvin is presented in table 3. Plot the data on the grid provided on page 17, circling the plotted points. So they've given you the data and they want you to ensure that you plot. Now, you see, the fact that they told you to circle, this is what they expect. All right. So they expect you to plot. This is 2 marks. How the marks are allocated, I can tell you that. All points on graph are 3 points correct, and the straight line through the origin gives you 1 mark. Correct axes, 1 mark. Because they would have given you a plain sheet of graph paper. So you must put in the axes to get a mark, and then you must plot all of the points, or at least 3 of the 4 points correct, and the straight line through the origin. All right. Using the graph in D part 1, calculate the rate constant for the decomposition of nitrogen 5 oxide at 333 Kelvin, stating the appropriate units. If you should use a ruler, if it's a straight line, yes, and it would be a straight line. All right. So they said using the graph, calculate the rate constant for the decomposition. No, they've given you pressure of the nitrogen 5 oxides versus rate of reaction. So rate divided by your pressure, which is equivalent, because it's a gas, basically to your concentration. So how would we use our graph in order to calculate K? The
Somebody
rate
saying
constant
the gradient.
yes, the rate constant would be the gradient of the graph. All right, and the gradient, the acceptable range would have been between 8.6 to 9.4 times 10 to the minus 4. So because we all draw our lines a little differently and read off a little differently, generally when you have to do calculations like these, it's a range that is given. All right, what would be the units? What would be the units?
So somebody's saying per second. Somebody's asking if the rate of reaction on the X or is the rate of reaction on the X or Y axis. Not so sure what.
It would be on the Y axis.
Okay, all right. So I'm seeing 2 more responses with per second.
Yes, that's the correct units. Sorry. All right. We are going to stop there.
Yes.
I know you must need. What I will do.
No, man, that's fine. That's fine.
Miss Dr. Taylor
Yes,
Campbell,
yes.
what
Yeah.
I can do, I will send the pages that I'd put together.
Yeah.
That I'd pulled the rate. Ooh, this one is ugly. What happened here? That I pulled from past papers.
Yeah.
From 2008 up to 2018 for rates. I will send it. I will send it to you so that it can be posted. I don't know how it will be disseminated, but I'll send the PowerPoint and I'll send the Word document to you so that it can be disseminated. All right.
Not a problem. Thank you. Okay.
Students, thank you so much for joining, and I hope it was beneficial, and I wish you all the best for the exam. Don't be nervous. Just go over what it is that you would have been taught and ensure that you solidify and you understand. Ask questions of your teachers, ask questions of each other so that you are ready and well prepared for the exam. All the best.
All right. So, students and colleagues, could you please show your appreciation for Mrs. Ellis Hall? All right. I'm sure they would love to get another session, but we have a Unit 2 session tomorrow. All right. So I'm not sure we can arrange for another Unit 1, but we'll talk, Mrs. Hall.
I don't remember when the exam is, but moderation is upon me.
Okay, yeah, I can just imagine. Sure,
Right.
sure.
So because of moderation and the very tight deadline
Yes.
for both CSEC and CAPE, I know my next 2 weeks are going to be
crazy.
Yes.
Yes, all right. Somebody was answering that it's the 1st of July. I probably they're talking about the exam.
1st of July? Wow, that's early.
Yes, that's very, very early. Well, we'll double check that so nobody has heart attack in this session. All right, so thank you very much, Mrs. Hall. Let's congratulate and thank our master teacher for this session. For those who are doing Unit 2, we will have a Unit 2 session tomorrow on alkanes and alkenes, right?
Yes, I'm going to do hydrocarbons. Hopefully we can get through both alkanes and alkenes.
Okay, all right. Great. Thank you. Thanks to everyone. And remember that the session is available on YouTube, so you can always go back to YouTube. Sorry, to check for the session. Right, so I was just explaining that it's on YouTube. Just type in Cape Chemistry Camp and you'll find the video, all right? I can still send the recording link, but since it's on YouTube, you can just go directly to that. Okay, thanks again to everyone for participating. Okay, thank you very much, Mrs. Hall.
Yes, a student was asking how will they get the document?
Okay, well, they had registered, so I can send directly to the emails that the persons who registered,
Okay.
as well as possibly to their teachers. So we'll see how that works out. All right.
Okay.
All right. Blessings. Okay.
I am going to email you right now so that I don't forget, because with everything being so crazy,
yes,
I don't want to forget. So I'll send it to you right now, the attachments.
All the best on your exams, students. Goodbye. All right. I'm going to close off now, miss.
All right.
Okay, all right. You can.
have some important information about a drug that a lot of people haven't heard about, ivermectin. What is it? Right. Ivermectin is a drug that has been around for at least 40 years. It was initially manufactured to treat river blindness and filariasis, these parasitic conditions or diseases that are common in parts of Africa and South America. But recently, it has been found to be useful against COVID-19.
In parts of India, it's been credited with bringing COVID-19 infections down to manageable levels.
Who found that out? Some scientists in Australia last year did a study and found that ivermectin
Oh, Jesus. Oh, God, I'm tired. My body is burning. Good afternoon, Miss. I declined your call. Let me explain because I was running a Cape chemistry camp for the Ministry of Education. So I was in the middle of I was in the middle of it. So it was supposed to be 2:30 until 4:30. Me just come out, Sharon. Me tired. Me beat out. And I have one tomorrow for Unit 2. And I don't finish that PowerPoint yet. So, oh God, I'm tired. Yes, miss. Virtual leaders, yeah. They're not even. I don't know. I don't know if any space because I went into my UE open email and saw that they said 150 more spaces. So I called you and didn't get you, and because I knew I had this thing, I called Kadra and told Kadra about it because Kadra didn't know either. Crystal, yes? Crystal? Crystal, are you hearing me? Crystal?